Hello, and welcome to my ISIT 2020 talk. My name is Christoph Höchle, and the title of the talk is Rényi bounds and information combining. Let us start directly. In all generality, information combining is concerned with any kind of combination of random variables, and here we limit us to 2 random variables. And even further, we're going to look at a very particular special case. We want to add these 2 random variables, and we're even going to restrict them to be binary. So we talk about addition modulo 2. This is a very common special case, and it has been proven very useful, for example, when investigating polar codes, belief propagation, or Shannon theory. Now, generally, or in the usual case, this is investigated in terms of the Shannon entropy. Now, if we simply have 2 binary random variables, we can, for each of them, assign a probability distribution. And if we add these 2 random variables, we get a new probability distribution that is simply the binary convolution of the original 2 probability distributions. Now, using that fact, we can easily describe the combined entropy of the random variables in terms of this function that is based on the binary entropy and only depends on the original entropy of the 2 random variables. Now, this is quite easy, but the whole picture becomes a bit more complicated if we look at site information. Now, instead of 2 random variables, we look at 2 pairs of random variables, here x1, y1, and x2, y2. And we aim to combine these on the x part. And we have, after combination, still all the previous site information available. So the entropy we want to look at is now the entropy of the combined x1 plus x2 given y1 and y2. Now, we want to find bounds on this quantity, again, only depending on the original entropy of the 2 pairs, or the original conditional entropy. And from now on, sometimes we're going to write h1 and h2 simply as shortcuts to simplify notation. Now, these are well-known information combining bounds. And for the entropic term we discussed, we get a lower bound that looks almost what we got in the unconditioned case, just that the entropies here are not the conditional entropies. And it's important that this is now only in lower bound. And we get a different looking upper bound, but also this one only depends on h1 and h2. Now, this lower bound is generally also known as the Mrs. Gerber's lemma, a very useful tool in information theory. And one more fact about these, we can think about x1 and y1 or 2 respectively as the input and output of a channel. And in that case, we know that this lower bound is achieved by binary symmetric channels, and the upper bound is achieved by binary eraser channels. Now, since the direction of these bounds will be sometimes different in the remainder of this talk, we're going to refer to bounds of this type as BSC bounds and to bounds of this type as BEC bounds. Now, we want to look at Rényi entropies. And up here we have the definition of the standard Rényi entropy. And this one is quite an undisputed definition. But now if we look at conditioning, the picture looks a bit different. In fact, there are many different definitions of conditional Rényi entropies. And I listed here only 4 of them, and these are going to be the 4 we consider in this work. But in principle, there are even many more. Now, all of them are different, and they have different properties. So in applications where they've all been useful, one often tends to just pick the one which has the properties needed for the setting one looks at. And so let's briefly look at the properties of these entropies. Generally, things that we would like to have are in particular that conditional Rényi entropies should converge to the Shannon entropy for alpha going to 1. We would like to have monotonicity in conditioning systems, and we would like to have a strong chain rule. Also, one can define a min entropy quantity, and we would usually like the conditional Rényi entropies to converge to this min entropy for alpha going to infinity. Now, unfortunately, none of the quantities defined on the previous slide satisfies all of these properties. The Arimoto version on the first line here gets the closest, but only satisfies a weak chain rule. A noticeable or one point and field here to point out is the third entropy, which does, as the only one, actually obey a strong chain rule. And this is going to be important later when we talk about an application. So now let's look at Rényi bounds and information combining. But before we do that, let's briefly review how to prove the information combining bounds in the Shannon case. So there are essentially two main tools, and the first one is simply noticing that any conditional entropy in the Shannon case can be written as a weighted sum of unconditioned entropies. We can, of course, do so also with the entropy we want to investigate. And what we get is unconditioned entropies that look exactly as the ones we discussed on the very first slide. Now, we know how to write the unconditioned entropy of a sum of random variables as something that only involves the individual entropies. And now the whole question is, how do we get these, the sum and the probabilities in the corresponding terms in this function? And of course, this can easily be done if we would know that this function is convex. And indeed, the convexity of this function is what was proven in the Mrs. Gerber's lemma paper. Now, knowing this, we easily get the lower bound, and it also can be seen that the convexity is enough to actually show the upper bound all through with a slightly different technique. Unfortunately, now if we look at Rényi entropies, already the first step doesn't work quite as easily. We don't have this relation in general. And in fact, we only have it for one of the entropies, the last one, to hold in this simple form. But now let's discuss how we go for conditional Rényi entropies and look at the Arimoto entropy. And while I mentioned that we don't have the simple form of writing the conditioned entropy in terms of unconditioned entropies, there's a somewhat more involved way of doing this. And this still looks kind of similar, or it seems like it fulfills a similar purpose, but we have these additional exponential functions in the definition here. And this leads us to defining auxiliary functions that are essentially the corresponding entropic function and also the exponential functions. And as in the Shannon case, where we had to go and observe certain functions involving the binary version of the Rényi entropy, we also here have to look at binary versions of this function k, which is simply the same exponential function of the binary Rényi entropy. Now, following the same ideas as in the Shannon theory case, Shannon entropy case, it now becomes quite easily clear that the function we want to look at is the one here on the bottom of the slide. So this is in structure, looks very similar, just that we have to replace the binary entropy by these binary Rényi k functions. And now it's important to show whether these functions are convex, in which case we would get very similar to bounds to what we have in the Shannon entropy case, or if these functions are maybe concave, in which we would get those bounds, but with the lower and upper bound interchanged. So based on the same strategy, or based on this strategy, we can actually find BSC and BEC bounds for the Rényi entropies. Now, let's say the function that we defined on the last slide is convex, then depending on the value of alpha, for the BSC bound, we get bounds that look very similar to what we had in the Shannon entropy case. Just that depending on the value of alpha, this is either an upper bound or a lower bound. And the BEC bound, again, if we assume convexity of this function, then we get bounds that are structurally somewhat similar, but they now explicitly involve these k functions. And again, depending on the value of alpha, it's either an upper or lower bound. And now I said, in order to get this, we need to assume that the function k is convex. If the function is concave, instead, the inequalities are exchanged. So following the same approach by defining auxiliary functions and then showing convexity or concavity of a certain function, we can also go ahead with all the other entropies I defined previously. And the general strategy is kind of similar for all of them. There may be only two things worth pointing out. The last one, the HC, is the only one which actually fulfills the property that we can simply write the conditioned entropy as a weighted sum of unconditioned entropies, basically identically to the Shannon entropy case. So in this case, we don't need an auxiliary function, and the function we're interested in is essentially the straightforward generalization of the Shannon entropy case. Another point worth mentioning is that for the second and the third conditional Rényi entropy, the same function here is crucial for determining the direction of the inequalities. So proving convexity or concavity of one of these two gives us the corresponding result for both of these entropies. Yeah, so now we have to look closer and when are these functions actually convex or concave to conclude the results of this work. And these are the results we present in the paper. And the first thing that should be pointed out is that in the Arimoto case, for the range from 2 to infinity, this can actually be extracted from an ISIT paper from 2008, where the authors considered generalizations of information bottleneck functions. So they look at a different problem, but one of the convexity of this function in this parameter range actually follows from one of their results. Additionally, we show that for the second case here, KH, which, as I mentioned in the previous slide, solves two of the Rényi entropy cases, we can determine convexity and concavity function in the whole parameter range. And also, by explicit construction here in yellow, we can show that in certain regions, the function can neither be convex or concave. Yeah, another thing to point out that we have these small flags here, 3 of them. And in these are the values where the function is convex and concave. So in fact, we have linearity, and that leads to some interesting results. Namely, we can actually show that the inequalities presented before, they actually all hold with equality for these particular parameters. So this might be very useful in applications, so I hope. And it's very remarkable as these equalities are something we usually only get in the unconditioned case. Okay, so far about the results in the work. Now let's briefly talk applications, and in particular the applications to polar codes. So I'm briefly going to summarize how polar codes actually work. The basic idea is that we first have a combining operation, which takes two channels, combines them via a CNOT gate. So here we essentially have the binary addition function. And after doing so, there's a splitting operation, which synthesizes from this combined channel a good channel W plus and a bad channel W minus. And they're called like that because the information transmission capabilities of these channels are either for the good channel at least as good as for the original channel, or not better than for the original channel for the bad channel. But at the same time, the overall amount of information that can be transmitted remains the same. So now it's very intuitive to see how polar codes work. If we reiterate this construction many times, then eventually we get some channels that work very well or close to perfect, and others that are almost useless. Now, this was proven in 2009 by Arikan, and the fact that we get perfect and useless channels is called polarization. And for the Shannon entropy-based neutral information, he proved this via martingales. So this is in principle a very nice proof, but unfortunately it's not as intuitive as one might hope. And it also doesn't tell us a lot about how fast this convergence happens, but only that it happens in the asymptotic limit. A couple of years later, Alson and Teleta provided a simpler proof, or conceptually simpler proof, using information combining bounds, in particular the Mrs. Gerber's lemma. And now it's probably quite easy to see how this, or why this works. The information combining bounds essentially tell us that there are additional terms here that strengthen these inequalities, and they mean that these inequalities are actually strict whenever the channels are not already perfect or useless. So every further combination step provides us with progress. Now, just last year, in a new paper, it was proven that this polarization also holds for mutual information based on Rényi entropies, in particular the J case here. But the proof was then again done via martingales. So now we can combine the Alson and Teleta proof from 2014 with our information combining bounds to simply show that that this particular Rényi entropy-based mutual information also polarizes. Polarizes. And another advantage is something that was introduced by Alson and Teleta as well, that while the standard proof for martingales was done when these two channels W are identical, this new proof also works if these two are actually different channels. And the same holds for our new work. So this quantity also polarizes if the channels are not identical. So this is just a brief example application. And now let me summarize the results of the work. So we have found new bounds on information combining in terms of Rényi entropies. In order to complete this argument, one needs convexity and concavity properties of certain functions. And in many cases, we have provided these properties. There are interesting special cases where equality holds, which hopefully has applications. And we would be very interested in seeing those. And we have briefly discussed applications to polar codes, so the polarization of Rényi entropies. Now, this work leaves some natural open questions. Of course, the obvious one is one could also look at other entropies. I mentioned there are even more Rényi entropies, but also other entropies like F divergencies. Or even better, maybe one can find a unified approach that handles all of them in, well, a simpler way. Also, we left open some convexity and concavity conjectures. And of course, these pose natural open questions. And since information combining bounds have been quite successful in information theory, it would be nice to also see more applications of these bounds. And with that, I'm looking forward to your questions, and thanks for your attention.